Hello, this is Dr. Jimbitsky and welcome to my environmental science screencast. Today we are going to discuss chemical isotopes. Hello and welcome back to the periodic table of elements. So today we are going to decipher together another great mystery of the periodic table. So let's pick a random element. We were talking about lots of different elements. For example, in the past we discussed carbon. So let's take a look. So here's our carbon, and carbon is element number 6, and this is what the atomic number is. It's number 6, meaning we have 6 protons in the nucleus of this atom. We also have the atomic mass, which is 12.01 daltons. So let's think about carbon. This is a picture from our textbook that shows the structure of the carbon atom. Nucleus is in the middle with 6 protons, which are shown here in red color. We have 6 electrons, which are distributed in 2 electron shells. We have 2 electrons on the first shell, and the outer shell will have the remaining 4 electrons. So 2 and 4 would be 6 electrons altogether. We also have here 6 neutrons, and the neutrons are shown in some type of a light color, right? It's like off-white or beige. So, what is the atomic mass of this element? The atomic mass is calculated by adding the number of protons and neutrons together. So I have 6 protons, I have 6 neutrons, so the atomic mass is supposed to be 6 plus 6, exactly 12 daltons. But now, let's think about what we saw in the periodic table. So in our periodic table, the atomic mass wasn't 12 daltons. It was something else, correct? So I'd like to remind you that the atomic mass in the periodic table was 12.01 atomic mass units or daltons. So where does this 0 or 1 come from? I cannot have 0.01 proton, I cannot have 0.01 neutron. And sometimes, if I ask this question in class, students tell me, well, we forgot about electrons, right? So we have 6 electrons. Maybe this is where 0.01 atomic mass units come from. But remember, one specific electron is a very, very light particle. So one electron is 2,000 times lighter than a proton or a neutron. So one individual electron mass is 1 divided by 2,000 atomic mass units. So that cannot possibly account for this 0.01. So that's not the answer. So the next question would be, is carbon atom unique? Is that the atom that has this number 12.01? Are there other atoms like this? So let's examine the periodic table again. For example, let's look at hydrogen. Hydrogen is the simplest element you can imagine. You remember hydrogen has 1 proton in the nucleus and 1 electron that spins around the nucleus. So here's our hydrogen. Again, the mass is not 1. It is 1.008. So we already talked about hydrogen, and we said that hydrogen doesn't have neutrons, right? So where does this 008 come from? That's a good question. That's a very mysterious question, and let's try to solve this puzzle together. We have other elements here right next to carbon, lithium, and beryllium, right? And if you look at their atomic masses, they're also not whole numbers. They're a number with a fraction that we either have to round up or round down. Now, what is the difference between hydrogen and lithium, or hydrogen and beryllium? Is the atomic number, which is a different number of protons. So if an element has one proton, it's gonna be hydrogen, right? So if an element has 3 protons, it's gonna be lithium. If it doesn't have 3 protons, it's not lithium. For example, if it has 4 protons, it becomes beryllium, etc., etc., right? So to be a particular element, I have to have a specific number of protons. So what about electrons? I can add and remove electrons, and that would create an ion, but it will be still an ion of the same element. So if I have a hydrogen atom, and I'm gonna separate one electron from hydrogen atom from the prior screencast, you know that in this particular case, I will gain an ion of hydrogen. But the element is still hydrogen. So if I'm going to change the number of electrons, that's not going to change the element, right? But electrons are not really important in calculation of the atomic mass. What is important are the protons and neutrons. Obviously, I cannot change protons. We all know that, because otherwise I will be making a totally different element. But the number of neutrons can be variable. So what does it mean? So if my hydrogen, for example, would have, instead of 0 neutrons, it would have 1 neutron, the mass of this hydrogen would be 2, right? And if my hydrogen would have, instead of 0 neutrons, 2 neutrons, then the mass would be 3. So what we see here in the periodic table of elements, in every cell of this periodic table, this number represents an average number of all atoms of a specific element in the universe. So what does it mean? So we may have hydrogens with different masses. Some of them will be 1, and some of them may be 2 or 3. But if we average it all together, we will end up with a number like this. So just imagine, for example, if you would like to measure weight of people in the classroom, right? Let's say it's an in-person class and we have like 25 or 26 students in the science lab. Now, we can ask everybody to step on the scales, and we can measure their weight. So then we can calculate the average weight. And how do we do that? We are going to add all the measurements together, and we're going to divide the sum that we will gain by the number of people in class, right? And that will give me an average weight of a person. So let's see, we calculated this weight. What are the chances that the average weight of a person will be exactly 170 pounds? It's probably very slim. Maybe it will be close to 170, but probably the average weight is not going to be exactly 170. Maybe it's going to be 170.2 pounds or something like this, right? So when we calculate an average number, most of the time we are ending up with a fraction like this. Now, in case of hydrogen, we may have variation of mass, but if we collect every single hydrogen atom in our environment, we add their masses together, and we calculate the average atomic mass, this is going to be this number. This is not a mass of a particular hydrogen, but rather an average mass of all the hydrogens in our environment. very similarly, over here, this is not a mass of a particular lithium atom. This is an average mass of all lithium ions in our environment. The same thing applies here. This is not a mass of a particular beryllium atom. It's rather an average mass of all beryllium atoms in our environment. That's why it's a fraction. So if you look at the periodic table, almost every element here has a mass which is a fraction. Well, we may find something like oxygen. Oxygen is right there, so let me zoom it in so we can see oxygen better. So oxygen, which is element number 8, has an atomic mass 16, right? But in real life, it's probably not 16. So in my periodic table, I have only two decimal spaces after this decimal point, right? I do not have the complete number because there is only so much room in this table. If I would have more precise average atomic mass of oxygen, I would have more numbers here after these 2 zeros, right? Because this is an average atomic mass of all oxygen atoms in our environment. So let's step back for a second and let's talk about this phenomena in more details. So what we see in our environment when we start looking at atoms of different elements, we can discover that each element may have different variations. And those variations of elements are called isotopes. So let's take a look at the definition of an isotope, right? So isotopes are atoms of the same chemical element with the same number of protons, but different number of neutrons, and therefore different atomic mass. What is important in this definition of isotopes is that it is the same element. And if isotopes are the same element, then they must have the same number of protons. Otherwise, it would not be the same element. But the number of neutrons can be variable. And if you add or remove neutrons, that will actually create a different atomic mass, which is a feature of isotopes. So different elements may have different number of isotopes. So for hydrogen element, we have 3 isotopes, which are shown here for your convenience. And those isotopes are called hydrogen 1, also known as protium, hydrogen 2, also known as deuterium, and hydrogen 3, also known as tritium. So why those elements, those isotopes of hydrogen, are called hydrogen 1, hydrogen 2, and hydrogen 3? Well, the answer is very simple, because of their atomic mass. The atomic mass of hydrogen 1 is 1 Dalton, or 1 atomic mass unit. The mass of hydrogen 2, guess what? It's 2 atomic mass units, or 2 Daltons. And the mass of hydrogen 3 will be 3 atomic mass units, or Daltons. Very, very simple. So when we are going to write chemical symbols for hydrogen 1, 2, or 3, we have to make those symbols different, so we know which one is hydrogen 1, 2, or 3. So hydrogen 1 written like this, H, and on the left side we are gonna put 1 as a superscript, and so this symbol indicates that we are talking about hydrogen 1. Hydrogen 2 will be shown like this. We will have on the left side of the element number 2 as a superscript. And hydrogen 3 will be written like this. We will have number 3 as a superscript on the left side of the letter H. hydrogen 1, hydrogen 2, and hydrogen 3. So let's talk about the structure of these 3 isotopes of hydrogen. Right here they are hydrogen 1, which is also known as protium, and the symbol will be this. Hydrogen 2, which is also known as deuterium, and this is going to be the symbol. And hydrogen 3, which is also known as tritium, and this is going to be the symbol. What is the difference? So hydrogen 1 will have 1 proton, right? Because it's hydrogen. Hydrogen 2 will also have 1 proton because it is still hydrogen. And guess what? Hydrogen 3 will have just 1 proton because it is hydrogen. So it has 2 protons, it becomes helium. If it has 3 protons, it becomes lithium, right? But all of these are isotopes of the same element, so they have to have 1 proton. Well, protium or hydrogen 1 has no neutrons, right? So what does it mean here? What is going to be the atomic mass of protium? So maybe let's write it down. So atomic mass of protium is gonna be 1 atomic mass unit or 1 Dalton, right? Because I only have 1 proton. So what is going to be the atomic mass of hydrogen 2? Well, you know it has to be 2 because it is hydrogen 2, right? But why is it 2? Because I have a neutron here. And so 1 neutron plus 1 proton is 2. So the mass of hydrogen 2 is going to be 2 atomic mass unit, 2 AMUs. And finally, I have hydrogen 3 here. Mass has to be 3. Why is it 3? Because I have 2 neutrons and 1 proton, right? 1, 2, 3. 2 plus 1 is 3. That will give me the atomic mass of 3 atomic mass units. So very simple and elegant. So what do I have here? I have hydrogen 1 with just 1 proton and no neutrons, right? It has 1 electron. And the atomic mass is 1 atomic mass unit. I have hydrogen 2 that has 1 proton and 1 neutron and 1 electron. And the atomic mass is 2 atomic mass units. And I have also hydrogen 3 that has 2 neutrons and 1 proton and 1 electron. And the atomic mass is going to be 3 atomic mass units. So now let's think about the average atomic mass. So remember, the average atomic mass was 1.001, something like that, right? So if I have atomic mass of 1, atomic mass of 2, and atomic mass of 3, how would I calculate the average atomic mass? I would have to add 1, 2, and 3 together and divide it by 3 because I have 3 isotopes here, right? So let's do that. So very easy. So 1 plus 2 and plus 3 is going to be 6. Is that correct? Right? And now if I'm going to divide 6 by 3, 6 divided by 3 is going to be 2 atomic mass units. Right? So 6 divided by 3 is 2 atomic mass units. So the average atomic mass has to be 2 atomic mass units. True or false? And the answer is false. Why? Because this will be true only under one condition. Only if these 3 variations of hydrogen, all the 3 isotopes, are present in equal ratio in our environment. So if 1/3 of all the hydrogens were like this, And another third of all hydrogen would be like this, and another third of all the hydrogen would be like that, then yes, the average atomic mass would be 2. But in real life, 99.9% of hydrogen atoms are going to be hydrogen 1 isotopes, like this, that have atomic mass of 1 atomic mass unit. And there will be very, very small percentage of hydrogen 2 atoms and very, very small percentage of hydrogen 3 atoms. And that's why if we are going to calculate the average mass, it is not going to be 2 atomic mass units. It's going to be close to 1, which is the mass of hydrogen 1. All right, so because our hydrogen 1, our protium, is the most abundant isotope out of the 3, 99.9% of all hydrogens in our environment are hydrogen 1 atoms. When I calculate the average atomic mass, it will be very, very close to 1. It will be just slightly higher than 1, but pretty close. Alrighty, so let's take a look what I have here for you. These are my 3 isotopes of hydrogen, right? So this is my hydrogen 1. On the left side, there is 1 as a superscript. This is my hydrogen 2. On the left side, I have 2 as a superscript. And this is how we would write it with a pen or pencil, right? And this is my hydrogen 3 with 3 as a superscript on the left side. So we already know that hydrogen 1 will have 1 proton, and hydrogen 2 will have 1 proton, and hydrogen 3 will have 1 proton as well. All of them will have 1 electron to keep the atom electrically neutral. I have 1 electron here, 1 electron here, and 1 electron here. Now, the only difference when we are talking about isotopes of an element would be the number of neutrons. So in this case, the number of neutrons is 0. In this case, the number of neutrons is 1. And in this case, the number of neutrons is going to be 2. Right? So if I'm going to calculate the mass, let's do that. If I'm going to calculate the atomic mass, what it's going to be. So in case of hydrogen 1, the atomic mass would have to be 1, right? Because I have only 1 proton here, right? And electrons are not part of the atomic mass. Now, what about my hydrogen 2? 1 proton and 1 neutron, 1 plus 1 is going to be 2 atomic mass units. And what about hydrogen 3? So it's very simple. I will have 1 proton and 2 neutrons. So 1 plus 2 is going to be 3 atomic mass units. So very simple and elegant. 1, 2, and 3. Alright, so here is our textbook, and so if I start reading the textbook, so here is the definition of isotopes. Alright, so that is very similar to what we have. And so this definition tells us that isotopes are forms of a single element that differ in atomic mass due to having a different number of neutrons in the nucleus, right? So this is pretty similar to our definition that we had before. It just worded slightly in a different way. Now, if we continue reading here, we will learn that many other elements have isotopes, not just hydrogen. And actually here are the isotopes of hydrogen, including hydrogen 2 and hydrogen 3. We will also, if we pay attention, we will also learn that oxygen will definitely have isotopes. So as you can see here, oxygen has 3 isotopes, which are called oxygen 17, oxygen 18, and oxygen 16. Guess which isotope of oxygen is the most abundant? Remember the atomic mass was 16, right? This is an average atomic mass. So what does it tell us? It tells us that oxygen 16 would be the most abundant of the 3 isotopes, right? And in our environment, there is only a small percentage of these isotopes, oxygen 17 and oxygen 18. So here we go. What I did here, I showed you these 3 isotopes of oxygen. Oxygen 16, oxygen 17, and oxygen 18. So let's name them. So this isotope is gonna be oxygen 16. So here we go. I labeled those isotopes for you. This is oxygen 16. We know it's oxygen 16 because it's written as 16 here as a superscript, and we know the mass of this isotope is 16. So this is oxygen 17. We also know it's oxygen 17 because I have 17 as a superscript, and I know that the mass of this isotope is 17. And I have also oxygen 18. I do know it's oxygen 18 because of this 18 as a superscript, and I know that the mass of this isotope is 18. So let's write down the mass as well. Here we go. I wrote it down for you. The mass of oxygen 16 is 16 atomic mass units. The mass of oxygen 17 is 17 atomic mass units. And the mass of oxygen 18 is 18 atomic mass units. So what I want you to do right now, I want you to pause this video, and I want you to grab a piece of paper and a pencil or a pen, and I want you to copy this screen that has oxygen 16, 17, and 18. And here is the number of protons, electrons, and neutrons for each of these 3 isotopes. And so similar how we had it for hydrogen isotopes, I would like you to calculate the number of protons, electrons, and neutrons for oxygen 16, oxygen 17, and oxygen 18. Alright, so I would like you to pause the video right now and try to complete this exercise with pen and pencil. Right? And so I trust that you truly will do this, right? Because otherwise it kind of defeats the purpose. And when you have numbers, and I assume that it's possible that some of those numbers will be correct and some not, but I am going to show you the answers in a second. But first, I want you to try to go through the process yourself so you practice. Okay, so let's pause the video and push a pause button on the video and do this exercise. Right, so at this point, please stop the video and do the exercise. All right, so did you have enough time? I trust that your video was on pause before I will reveal correct answers. And here are the correct answers. You know that oxygen is element number 8 in the periodic table. What does it mean? It has to have 8 protons in the nucleus, right? No matter what kind of isotope of oxygen it is, it must have 8 protons, otherwise it's not oxygen. The number of electrons is also going to be 8 to keep this element neutral. Now, what about the number of neutrons? This is a difference. The number of neutrons is the difference for the isotopes. Now, this mass is 16, and the mass is combination of protons and neutrons. So I have 8 protons, so 16 minus 8 is 8 neutrons. How about over here? The mass is 17. 17 minus 8 protons will give us 9 neutrons. And how about over here? The mass is 18. So 18 minus 8 protons will give us 10 neutrons. So the difference between these 3 isotopes is the number of neutrons. I have 8 neutrons in oxygen 16, 9 neutrons in oxygen 17, and 10 neutrons in oxygen 18. And I think we discussed it already, that the most abundant oxygen isotope is oxygen 16. Very similarly, the most abundant isotope of hydrogen is hydrogen 1, which is shown over here. So the question is, why we have these differences? Why some isotopes are more abundant and some isotopes are less abundant? So why, for example, in our environment, we have a lot more hydrogen 1 compared to hydrogen 3? And the answer is really very simple. This is because of one simple reason: different stability. Some isotopes are more stable, and so they can exist for a longer time, and some isotopes are less stable. So what happens if the isotopes are less stable? So they can decay. And when they decay, they can lose some subatomic particles, right? So they can lose some protons, or they can lose some neutrons, and they can become a different element. And this is possible. Another important moment here is that some of the isotopes, when they decay, they emit radioactive energy. So, for example, hydrogen 1 and hydrogen 2 are regular isotopes of hydrogen, but tritium, or hydrogen 3, is a radioactive isotope because when it decays, it emits radioactive energy. So some isotopes are radioactive isotopes because when they decay, they emit radioactive energy. So radioactive energy can be pretty dangerous for human health, but it can be also quite useful. And some isotopes can be used in medicine and research, and some radioactive isotopes of uranium can be used to produce electricity inside of nuclear power plant. And that's why it's very important to know about isotopes in our environment. We cannot see radioactivity, and for a very long time, we did not know about radioactivity and radioactive isotopes because you need to have special equipment to detect radioactive energy. This is not something you can see with the naked eye. And so when I teach my in-person class, I always ask my students, does anybody know who discovered radioactivity? And very unfrequently, actually, I have somebody in the audience who does know. So let's talk about the discovery of radioactivity. The person who discovered radioactivity was Marie Curie. Marie Curie is a French scientist who was born in Poland, and then I think she married a French person and she moved to France, and this is where she did her research and discovered radioactivity. And because she's a French scientist, very frequently we call her Madame Curie. Now, discovery of radioactivity is extremely important achievement. And another reason why I would like everybody to know about Marie Curie, because she is the first female scientist who ever was awarded a Nobel Prize. And so she actually received the Nobel Prize twice. The first time for her discovery of radioactivity, she received a Nobel Prize in physics. And then later, when she did more research using radioactive elements, she received another Nobel Prize in chemistry. So it's quite outstanding person, and please remember that women in science, it's a relatively new phenomenon, right? And so here we are looking like at early 1900s, and at the time there were not that many women in science. Here we are looking at historic photograph of one of the scientific conferences when physicists gathered to discuss, some important topics in physics. And if you look at the composition of this group, so scientists are males. With one exception, there is Marie Curie over here, the only female. She's Marie Curie, this lady, Madame Curie, the first female scientist who received a Nobel Prize in physics. So absolutely outstanding person, and everybody should know about Marie Curie. This is a research institute building in Paris. You can see this building belongs to the University of Paris, and this is where Marie Curie lab used to be. And another question that I ask when we talk about Marie Curie, I ask my students if they know why did she die. Marie Curie died of leukemia, and you probably know that leukemia is a type of the blood cancer. And why she died of blood cancer? Why did she develop leukemia? This is because of her research and handling of radioactive isotopes, which are very, very dangerous for human health. But because Marie Curie was the first person who discovered radioactivity, at that time, the danger of radioactive energy to human health or living things in general was not known. As a matter of fact, nobody had even a slightest idea what radioactivity or radioactive energy was. And so when Marie Curie worked in her laboratory, so she pretty much handled radioactive isotopes with her bare hands. And this is not because she didn't want to protect herself. She just didn't know about the danger of radioactive energy, and nobody knew at that time. So now when a scientist works with radioactive isotopes in the lab, they have to follow all the lab safety procedures, and they have to wear personal protective equipment. And depending on what kind of element it is, there are different ways to protect yourself. So for example, if you are working with hydrogen 3, so hydrogen 3 is right here. So as a reminder, hydrogen 3 is a very, very weak source of radioactivity. And imagine if you put a piece of paper between yourself and the source of radioactivity and tritium. A piece of paper would be enough to shield you from radioactive energy that is emitted by tritium. So as far as you're wearing gloves, as far as you're not eating or drinking in the lab, and not touching tritium with your bare hands, you're protected, right? Now, some other isotopes emit a lot stronger radioactive energy. For example, uranium that we use inside of the nuclear reactor. So the radioactive energy from uranium is so strong that you have to shield yourself with a concrete wall. And so obviously a sheet of paper is not going to protect you from radioactivity emitted by uranium. So there are different types of radioactive isotopes, and they may have different strengths of radioactive energy, and there will be different type of precautions. So obviously some of those isotopes can be used to produce electricity, such as isotopes of uranium. Tritium, hydrogen-3, is very commonly used in biological research because many biological molecules contain hydrogen. So if you have a molecule that has hydrogen, and instead of regular hydrogen you use hydrogen-3, you can actually detect what happens with this particular molecule. You can trace how this molecule is changing in the body, because you may have special equipment that will help you to detect this element, right? So very frequently, for example, we use radioactive hydrogen-3 to study DNA synthesis in a cell. And so DNA is a molecule that contains hydrogen, and DNA also a hereditary molecule, right? This is where the genetic information is stored. So scientists use hydrogen-3 isotope to study how the cell makes more DNA molecules, for example. Now, some isotopes can also be used in medicine. For example, to study the functions of different organs. So, for example, to study the function of the thyroid gland or function of kidneys. And so certain isotopes can be injected into the bloodstream, and then with a special equipment, the doctor can detect where in the body a particular isotope is, and that can help us to diagnose a certain type of medical conditions. So for many practical applications, it's very important to know how strong is radioactive energy and how stable a particular isotope is. So, and this is not only important in medicine to diagnose particular medical condition, but also to know how to store and handle the isotopes safely, right? Obviously, you will not want to have uranium injected in a person. We know that hydrogen-3 is a lot weaker isotope compared to uranium, but you also don't want to inject hydrogen-3 into a person because it will get incorporated in the DNA, which is hereditary information, right? And it can damage DNA and cause mutations, which is not a good thing. So change in genetic code that will cause mutations very frequently causes cancer and other genetic abnormalities. So you probably will not want to use tritium for medical procedure. You will have to look for something else. So when we look at different isotopes, we would like to know how stable a particular isotope is, and that will help us to decide how we can use this isotope, or how we can store it, or how we can dispose it, etc., etc., etc. And also we will know how to protect ourselves. So to understand better what's going on, we have to look at so-called half-life of radioactive isotopes. So the half-life of radioactive isotopes tells us how stable or not so stable a particular isotope is. So let's take a look at the definition of half-life and how half-life can help us to understand the stability of different isotopes. All right, so the rate of radioactive decay is a characteristic of each radioactive isotope. So each radioactive isotope will have a different radioactive half-life. Okay, does it make sense? So now let's continue reading here. So scientists talk about this rate as a radioactive isotope's half-life, commonly referred as just half-life. It is the time requires for disintegration of 1/2 of radioactive atoms that are present when measurements start. Okay, so what does it mean, disintegration? So remember, if we come across some type of unfamiliar words, where do we go to look those words up? We go to the Merriam-Webster College Dictionary, okay? And at this time, we would like to look up the meaning of this word, disintegration. So let's do that. We are back to our very well familiar Merriam-Webster dictionary, and we already know how to use it. So, and this is a word, disintegration. All right, so pretty much to disintegrate means to break down something, right? So when you have an isotope, when we say an isotope is disintegrated, it decayed, it is broken down, and we don't have it anymore. All right, so we are back to our slide here. So the half-life of radioactive isotope will tell us what period of time is necessary for 1/2 of the radioactive atoms to disintegrate, to decay, to be gone. All right, so it's important to remember that this number is not representing a fixed number of atoms that disintegrate, but a fraction, okay? Half, 50%, the period of time which is necessary for half of the atoms to disintegrate. So let's take a look at specific example. For example, if there are 100 atoms of radioactive isotopes that has a half-life of 1 minute, there will be 1/2 of this number, or 50 atoms of the original radioactive isotope, left after 1 minute, right? Because the half-life is 1 minute. So how many atoms I will have after 2 minutes? After the second minute, I will have 25 atoms of the original radioactive isotope left, right? So the fact that this simple example points to the existence of 12.5 radioactive atoms after 3 minutes illustrates that half-life is intended to be used for a very large number of atoms that are found in even small samples of radioactive material, because 100 atoms, this is not really a lot, right? So 100 atoms is a very, very small quantity. And so where did this 12.5 radioactive atoms come from? Because after 2 minutes we have 25 atoms, right? After another minute passes, another minute, half of 25 will disintegrate, and what we will have, 12.5. Okay? So in a nutshell, if we think about this, so the half-life tells how quickly radioactivity from the radioactive isotope will decrease, okay? And radioactivity can be measured in the units which are called curies. And actually, curies are units of radioactivity, and this word has to be capitalized because it's after Marie Curie, right? So we may have some isotopes which are more stable or less stable. So the longer is the half-life, the longer time it will take for the isotope to decay, and so the more stable it will be, and the other way around. Very well, so let's summarize what we know about radioactive half-life. So radioactive half-life is time required for a given amount of radioactive isotope to decay or disintegrate in half. All right? A period of time required for a given amount of radioactive isotope to decay in half. And different elements will have different half-life. So, for example, radioactive half-life of hydrogen-3 is 12.5 years. So what exactly does it mean, 12.5 years? So imagine that today we have 100 grams of tritium. Right, tritium is the name for hydrogen-3. So 100 grams, this is actually a very large quantity of tritium. So for comparison, your pencil may have a mass of maybe 5-7 grams, right? So 100 grams is quite substantial mass, right? So, but I'm just saying 100 grams because 100 is a nice number to do calculations. All right, so imagine that today we have 100 grams of hydrogen-3, tritium. So how long I have to wait for this amount to decay in half? So how long do I have to wait to have 50 grams of tritium? I have to wait a half-life, because a half-life is a period of time required for a given amount, which given amount is 100 grams here, of radioactive isotopes to decay in half. So what does it mean? After 12.5 years, I will only have 50 grams of tritium left. Now, how long do I have to wait to have 25 grams? So I have to wait another 12.5 years. From today, it's going to be 12.5 years and another 12.5 years, which is 25 years, right? So after 25 years, I will have 25 grams of hydrogen-3 or tritium. And how long do I have to wait to have half of this, 12.5 grams? I have to wait another 12.5 years. So from today, it's going to be 37.5 years. So what does it tell us? Hydrogen-3 or tritium is extremely stable isotope, right? So if I would be using this isotope for medical procedure, and I would give this to a patient today, I inject to, check something for a medical test, 37.5 years from today, I will still have a lot of these isotopes in the body. So I will not want to use this for a medical test, right? So if I'm going to use this for medical research or biological research, for example, to study synthesis of DNA molecules in the cells, I will have to make sure that when I dispose the radioactive waste after my experiment, that I can store it securely, because even after almost 40 years, these isotopes will be still present. It's not going to decay completely. So it is quite stable. So what kind of isotope we would like to use for medical procedure? Well, here's another isotope. This is an isotope of iodine. Iodine is another element from the periodic table, and this particular isotope, which is frequently used for various medical procedures, is iodine 131. So the mass of this iodine is 131 atomic mass unit. And this isotope has a lot shorter half-life, 8 days. So let's see how fast it will disintegrate or decay. So imagine that today, similar to our first example, we have 100 grams of iodine 131. How long do I have to wait to have only 50 grams. I have to wait half-life because my given amount, 100 gram, will decay in half during the half-life, which is 8 days. So 8 days later, I will have 50 grams of iodine 131. How long do I have to wait to have 25 grams? Have to wait another half-life, which is going to be another 8 days. That's going to be 16 days from today. And how long I have to wait to have half of that, 12.5 grams. I have to wait another 8 days, which is going to be 24 days from today, right? So this isotope will decay a lot faster compared to hydrogen-3 isotope, right? Remember, it would take 37.5 years for 100 grams of hydrogen-3 to decay to this state, 12.5 grams. And here it's about 24 days, which is actually less than a month. So these isotopes would be a better isotope to use for medical procedure. It's not going to sit in the human body forever and ever and ever. Of course, if you think about a period of time of 24 days, it is still kind of long, right? And you wouldn't want to have radioactivity in your body for 24 days. But when we talk about any kind of a medical procedures, there are pros and cons, right? Even if you go to a dentist and they would like to make x-rays of a tooth, that has some negative consequences, right? If they don't appropriately protect your chest, for example, with a lead apron, or if you had too many x-rays a year. So, however, in case of isotopes that we use for medical procedures, not only the radioactive half-life is important, but also how fast a particular isotope is eliminated from the body. So let's take a look at this information here. So besides radioactive half-life, we also have something which is called biological half-life. So let's take a look at the biological half-life. So the biological half-life is the time an organism takes to eliminate 1/2 of the amount of a compound or chemical on a strictly biological basis, right? So thus, if a stable chemical compound were given to an individual and half of it were eliminated by the body, so perhaps in urine within 3 hours, the biological half-life would be 3 hours. So when we are talking about any kind of chemical, if it's not even a radioactive chemical, right, it will have a biological half-life. And that would be also true about drugs, because drugs are compounds, drugs are chemicals, right? And certain drugs can be, for example, eliminated from the body with urine. And certain drugs we need to take with certain frequency. Some drugs are taken once a day, and some drugs are taken 2 times a day or 3 times a day. And it all depends how fast they're eliminated from the body, right? So this is your biological half-life, a period of time that is necessary for the body to eliminate some type of a chemical. So if the isotope is still present after 24 days, but it is eliminated from the body, perhaps in urine, that it doesn't really matter because, the isotope is not in your body anymore, right? So, and biological half-life is another thing that we have to look at when we are using radioactive isotopes for medical tests. Scientists also have something that is called the effective half-life. And the effective half-life is pretty much a combination of radioactive half-life and the biological half-life. Okay, so if you look at the definition of the effective half-life incorporates both the radioactive and biological half-life. It is used when health physicists calculate the dose from internal radiation source to determine the effective half-life of radioactive isotopes. In a human, one needs to know the radioactive half-life as well as biological half-life of radioactive isotope. Right, and so here we are talking about the internal radiation source, right, which can be as a result of a medical procedure, for example, or it can be also a result of unexpected exposure to radioactive isotopes. Let's see, for example, we are talking about some type of an accident in a nuclear power plant when a person didn't expect to, but unfortunately was exposed to some radioactive isotopes, and they can be present in the body. And so it's very important to look at the effective half-life, which is the way how to combine the radioactive half-life and biological half-life together. So I hope that now you have a good understanding of radioactive isotopes, and you also know who Marie Curie was and how important she was as a scientist, because her work gave us radioactivity understanding. We have isotopes that can be used for different applications, from production of electricity in the nuclear power plants to different types of medical procedures and research. If you have questions, you know how to get in touch with me, and I will talk to you soon.